The next topic is cooperation in ad hoc networks. Cooperation, as we have seen in the introduction, is a very important issue, a very important topic when it concerns ad hoc networks. Without cooperation, without successful cooperation between the different nodes in the networks are not going to survive at all. So, let us look at the different ways in which cooperation is ensured in ad hoc networks. So, before we do so, let us first review some of the characteristics of ad hoc networks. So, this is what we have already seen. We know that ad hoc networks operate, the nodes in the networks, they operate in the wireless environment, wireless medium. They are mobile, the nodes are mobile, there is no definite structure of these networks. So, basically the collection of nodes, they are going to talk to one another, and there is no one topology that governs these networks. The nodes could be heterogeneous, having different specifications. They have, the ad hoc networks, they basically exhibit autonomous behavior. That means they should be able to, to survive on their own. They should be able to operate on their own, and whenever there is some kind of abnormality, they would be able to survive through such kind of situations. Multi-hop radio relaying is another that we have already seen. Distributed operation for security, routing and host configuration is another property. So, I do not need to elaborate this, we have already understood this particular aspect. Dynamic network topology is another. Energy constrained behavior, mobile and spontaneous behavior, intermittent connectivity, and the different nodes in the networks are prone to different types of abuse, different kinds of attacks, and so on. These are some of the typical characteristics of mobile ad hoc networks. Let us look at some of the challenges in enabling these networks. So, all these things we have already gone through. So, let us just review them quickly. So, the first is the limited bandwidth of the environment, dynamic changes in the topology. So, the nodes are supposed to be very mobile in a MANET particularly. So, the topology is also going to be made and broken quite fast and reformed faster. So, routing overhead is another. So, because whenever the nodes move, the topology changes, and there is going to be overhead in discovering the routes once again and maintaining the route information at the different nodes. So, all these things basically bring in a lot of routing overhead. Hidden terminal problem, this is something that we will look at when we when we look at medium access control, hidden terminal problem and the exposed terminal problems. Packet losses due to transmission errors, mobility induced route changes, battery constraints we have seen already in the introduction. So, there are different severe constraints on energy consumption in these different nodes, because the battery have very small amount of energy that comes with them. Security threats and uncooperative behavior of the selfish nodes. Now, in this particular backdrop, that means that we have looked at the characteristics of MANETs, we have looked at the different challenges in implementing MANETs. So, in this backdrop, we have to understand the issue of cooperation. So, before we do that, we need to understand that the nodes in MANETs, they may operate ideally, they may operate properly, or they may not. So, based on the behavior of the different nodes, these nodes in MANETs, they can be classified into two categories, unintentional and intentional. In the unintentional category, we have the failed nodes and the badly failed nodes, whereas in the intentional category, we have selfish nodes and malicious nodes. So, let us look at each of these different types of node behaviors, each of these different types of nodes, and what they mean in more detail. So, failed nodes are simply those which are unable to perform an operation maybe due to different reasons such as power failure, or maybe there is some kind of an environmental condition, an environmental event that has made a particular node to fail the way it is supposed to do. The second is the badly failed nodes, which basically exhibit features of failed nodes, but they also send false routing messages which can be a threat to the overall integrity of the network. The selfish nodes are typically those which basically are willing to cooperate initially, but later on they are unwilling to cooperate. So, initially they are willing to cooperate, but later on due to their different constraints, such as they have very limited energy in them, they have very limited computational power and so on. So, initially they agree to cooperate, but later on they do not cooperate, right. So, they are unwilling to cooperate because they want to be miser, they want to save their own limited resources, and they do not want to help the other nodes in routing their messages through them. So, packet dropping is the main attack that is done by the selfish node. So, what it means is a selfish node, when it receives a packet, because initially it agreed to forward the packets. So, when it receives the packet, then instead of forwarding it to the next hop neighbor, what it is going to do is it is going to silently drop the packet, okay. And that is the selfish node. So, and the other nodes are not going to know that it has in fact dropped the packet, right. And malicious nodes, basically what they do is, unlike the selfish nodes, these nodes they do not do it silently. What they do is they deliberately disrupt the correct operation of the routing protocol or other protocols that are running in these different nodes, thereby denying network service if it is possible, okay. So, there are different characteristics of the selfish nodes, and these were enumerated in a work published by Marty et al. In Mobicom conference in 2000. So, as per their definition, selfish nodes are the ones which exhibit characteristics such as they do not participate in the routing process, they do not reply or send hello messages, and they intentionally delay the RREQ packet. We will see what it means by RREQ and RREP. So, RREQ means the route request packet, and RREP means that route reply packet. So, whenever a route request packet arrives, they would intentionally delay forwarding them, or whenever there is a RREP, the route reply packet that arrives at a particular node, they would delay forwarding it. So, these are the behaviors of the selfish node. The other one is dropping of the data packet that we have already seen. So, whenever a selfish node receives a packet, instead of forwarding it further, these nodes are going to drop the packets. So, the advantages that are gained by the selfish nodes are like this, that they exploit the service of the cooperating nodes. So, there are other nodes which cooperate. So, these selfish nodes, whereas they are enjoying the services that are offered by the other peers which are cooperating nodes, these nodes they do not actually cooperate in turn with these cooperating nodes, okay. So, they do not reciprocate in terms of cooperation. They exploit the incentive measures to gain monetary benefits, and they preserve the resource and power, and they prevent other nodes from getting proper service. So, these are some of the advantages that are gained by the selfish nodes. To deal with these misbehaviors, the scientists Marty et al. Again in the paper published in Mobicom in 2000, what they have done is they have tried to propose a solution. So, in their work, what they do is they define misbehaving nodes to be the ones which initially agree to cooperate, but eventually they do not. So, what they do is, in their solution, they intelligently try to identify the misbehaving nodes and avoid relaying through these particular nodes, these specific nodes. So, what is important is to identify which nodes are misbehaving, and then it is obvious that once the nodes are misbehaving, just avoid them while routing decisions are made. That means, avoid them through the routing paths when these routing paths are determined, okay. So, in their solution, they primarily use two components. One is called the watchdog, which basically runs on every node to keep track of the behavior of the different other nodes in its proximity. So, every node runs a watchdog process, and that watchdog basically the task of the watchdog is to keep an eye on the behavior of the neighbors of that particular node. And based on the information that is supplied by the watchdog, every node finds out what are the reliable routes to the other intended destination nodes in the network, and that is done through the component which is known as the path rater. So, there are two components, watchdog and the path rater. So, the watchdog basically detects misbehaving nodes by overhearing transmission. Okay. So, let us look at the figure in front of us. So, what we have is a multi-hop scenario. We have a source node and a destination node. The source node intends to send the packet to the destination node D via the intermediate relay nodes A, B and C, via A, B and C. So, what it is going to do is sends to, let us say, A. So, A and every node, that means B, C, D, etc., what they also do is they all of them in the network, they would maintain a buffer of the recently sent packets. All of them, they are going to maintain a buffer of the recently sent packet. So, let us say that A sends the packet to B, it forwards the packet to B. So, then what it B does is B would in turn forward the packet to C after it has received it. So, when this is forwarded to C, node A, because it is within the transmission range of node B, because it is a neighbor of B, overhears this particular transmission. So, when it overhears this transmission, then it basically, what it does is that buffer information that it had or originally when it had sent that packet to B, it is going to delete it. It is going to remove that particular information, because it is now confirmed that B has sent it forward, right. So, basically, so it would compare, node A would compare each overhead packet with the packet in the buffer to see if there is a match. If the packet remained for longer than timeout, that means that it is likely that B has not forwarded it, right. So, if it has remained longer time than the timeout, then it increments a failure tally, that means some kind of table it is going to maintain, a tally table for the node that is responsible, that means in this particular case node B. So, it is going to do that, and if the tally exceeds a threshold, the node is determined to be misbehaving and the source will be notified. So, what A is going to do is it will observe for certain duration of time or certain number of times, how many times node B, for example, is not forwarding. So, it could be that, one instance may not suggest that node B is a malicious node or a selfish node or a misbehaving node in general. So, it might be that due to some other reason node that overhearing that was supposed to happen for the B's transmission at A, that has not taken place. So, that so one or two instances that may not suggest. So, there should be some number of times, certain number of times, a preconfigured number of times, a threshold number of times, that if such a phenomena occurs, then node B can be tagged as a misbehaving node, otherwise may not be that the node B is a misbehaving node. So, the advantage, this particular mechanism by which the watchdog operates, it is advantageous because this way one can detect misbehaviors at the forwarding level, but this approach also comes with different disadvantages. So, let us look at different cases where such a mechanism may not actually detect the presence of misbehavior. So, let us look at some of these. Okay. So, ambiguous collision is the first case. So, as we can see over here, So, what might happen is there could be some kind of collision that might happen at A. So, what might happen is that when B, so A has sent to B, B has forwarded to C, and a copy of that message that B has sent to C is overheard by node A, but when A receives that overhearing message, maybe another packet arrives from S, the second packet, and there is a collision at A's end. So, due to that collision, so A would not be able to overhear the transmission from B. Let us look at another scenario, the receiver side collision. So, in this particular case, as we can see that A forwards the packet to B, B forwards to C, A overhears that, but when C gets it, there is another packet that was sent by D. So, at the receiver side C, there is a collision between the packet that is sent by B and the packet that was sent by D. So, there is a collision between these two packets. So, consequently, node A can only tell whether node B sends the packet to node C, but it cannot tell in this particular scenario, for example, that node C has actually received it or not. Okay. Node A cannot tell it. It can only confirm that node B has sent it, but it cannot really confirm whether node C has received the packet. Limited transmission power is another issue. So, the misbehaving node can control its transmission power to circumvent the watchdog. So, what it means that a node could limit its transmission power such that the signal is strong enough to be overheard by the previous node, but it is too weak to be received by the true recipient. So, it can control, so because the more transmission power with which the packet is sent, the more number of nodes in the proximity would be able to receive the packet. So, this particular node, it can basically manipulate it so that the true recipient does not receive, but the watchdog actually thinks that it has received. Okay. So, actually, so this is some kind of getting around the watchdog, right. So, this would require that the misbehaving node knows the transmission power that is required to reach each of its neighboring nodes, and that is an assumption under which this kind of scenario might occur. False misbehavior. So, here as we can see that what might so happen is any node over here, it can falsely report to the other nodes that one of its neighbors is a misbehaving node, because it is so there is some kind of trust that goes on between the different nodes. So direct so particularly so for instance so A might report to S, that node B is a misbehaving node, and there is no way that S can ensure whether A is reporting correctly about the behavior of B or not. Collusion. Collusion means that couple of nodes together, they are going to collude, they are going to form some kind of a group, and they are going to launch the attack. So, let us look at the figure on the slide. So, as we can see over here, the nodes B and C, they can collude, that means they can group together to launch a more powerful, a more sophisticated attack. So, in this particular case, B forwards a packet to C, but does not report to A. B sends to C, but it can manipulate in such a way that it does not report to A when C drops the packet. When C drops the packet, so B will come to know about it, whether C has dropped the packet or not, whether the packet that was sent by B has been received by C or not. B will come to know about it, but if B is also malicious, I mean not malicious, misbehaving, then together what it can do is it will not report to A. So, A will not come to know that whether B and C together have launched some kind of a collective misbehavior. So, that is why it is suggested that because of this limitation, it is suggested that one should disallow two consecutive untrusted nodes in a routing path. So, so if B is also untrusted, not a trustworthy node, C is also not a trustworthy node, then two of them successively should be avoided in a particular routing path. Partial dropping is a case where a node can circumvent the watchdog by dropping packets at a lower rate than the threshold. So the rate at which, I mean, there is some kind of a threshold that is maintained by the by the watchdog. So so if you if you basically drop the packets at a lower rate than that, then the watchdog will never be able to know about whether any node is misbehaving or not. So we have seen how the watchdog behaves, how the watchdog can keep an eye on the behavior of the different nodes around it, and we have also seen that this kind of approach that is adopted typically by the watchdog can be circumvented, can be manipulated, and we have seen the different scenarios under which the watchdog mechanism that we have explained that may not work properly. So, assuming that it works properly and the watchdog has keeps an eye on the behavior of the different nodes in its vicinity, that information is collected, the watchdog information is collected by the other component in multi-atal solution, which is known as the path rater. And what the path rater does is, so each node maintains a rating for every other node it knows about in the network. It calculates a path metric by averaging the node ratings in the path. The metric gives a comparison of the overall reliability of the different paths, and if there are multiple paths to the same destination, it then chooses the path with the highest metric. So, what does it mean? That based on the observations by the watchdogs, watchdog processes running at the different nodes in the network, the path rater is going to collect that information from these different watchdogs, and then it is going to determine that which path or paths are the most reliable ones, that means where the nodes are least trustworthy, least non-trustworthy, that means more trustworthy nodes are resident. I mean, so it will determine those paths and it will forward, the path rater will then forward that information to the nodes, so that the nodes forward the packet only through those paths which are more reliable ones, that means which have least number of untrustworthy nodes. So, there are different incentive mechanisms that have been proposed for cooperation. One of these was proposed by Batian and Huber in 2000-2001, where they talk about providing different kinds of incentives in the form of reward penalty without overloading the network. So, in their reward penalty model, they propose charging the nodes that receive a service, remunerating the nodes that offer the service, and then based on the above model, that means charging remunerating model, accepting or rejecting a relay request that comes to a particular node. Okay. So, charging the node receiving the service, remunerating the nodes providing a service, and accepting or rejecting a relay request based on this particular model. So, the drawback is that there is large overhead in a resource constrained ad hoc sensor network if we adopt this kind of reward penalty based model, because large number of packets, unnecessary packets, control packets are going to fly all around in the network. That leads to, that is undesirable, because already the network, these kind of networks are resource constrained, and we do not want to overload these networks even further. So, there are two types of systems, two types of solutions that have been proposed in the literature. One is called the virtual currency system and the other one is called the reputation system. Virtual currency systems belonging to this category are two types of systems called the nuggets and the sprite, and the reputation systems examples are confident, core and ocean. So, in virtual currency systems, these systems use some form of incentive to compensate for the service that is offered by a node. A node basically receives a virtual payment for serving the network and it uses the incentives to gain service from the network. Okay. So, basically that a node would basically get paid when it is serving the other nodes in the network in the form of some kind of a virtual payment, and that is the incentive that it gets, that if I forward the packet of another node, I am going to get served, I am going to get some kind of a payment, and it is that payment that serves as the incentive for this particular node to serve the other nodes for forwarding their packets. So, nuggets and sprites are examples belonging to this particular category, that means the virtual currency systems. So, with this we come to an end of the first module. In the next module on cooperation, we will be continuing with the virtual currency systems, then we will talk about the reputation systems and we will look at some of the protocols that have been proposed for each of these classes of systems. Thank you.